Hello. In this section of the course we're going to be looking at the theory of numbers. Number theory is really the theory of integers rather than general numbers, and it's one of the oldest branches of mathematics that there are. Possibly geometry is older. It's hard to tell, of course, at this distance. The one difference that people always see between geometry and number theory is that number theory is usually reckoned as not of as great utility as geometry is. The great 20th century British number theorist G.H. Hardy took great pride in the fact that his work had no utility at all. Fortunately, Hardy has been proved wrong. One of the things that happened during the end of the 20th century was that we found many applications of number theory. You use number theory yourself every time you take money out of an ATM, every time you buy anything on the internet, every time you get a computer, for example, to factorize polynomials or do an integration. Number theory is behind everything that you do. In fact, number theory has even found applications in the acoustics of concert halls. In MATH1081, we're only going to be looking at the very basics of what is a huge topic in mathematics. We do run later year courses that talk a bit more about other branches of number theory and other applications. MATH2400, for example, and MATH3411, that's finite maths and information codes and ciphers. They look at the applications of number theory to such topics as cryptography and digital communication. Our other third year course, MATH3521, Algebraic Techniques in Number Theory, as the name suggests, looks at applying algebraic techniques to a number theory, and in fact that course ends with looking at applications of number theory to questions of pure geometry. As I said, we're all going to be looking at the very basics in this particular course, and we're going to begin by introducing some notation. So our first piece of notation is Z+, the positive integers, the numbers 1, 2, 3, and so on. The natural numbers, well, that's Z plus including 0, 0, 1, 2, 3, and so on. The integers themselves, 0, plus and minus 1, plus and minus 2, plus and minus 3, all the way up to positive infinity and down to minus, that's the set of integers. The set of rational numbers, which we denote with this symbol Q, are all numbers of the form one integer over another. We typically assume that the denominator is positive and the numerator could have the sign. It doesn't really make much difference, but it's more convenient to do things that way. And the other two sets that you might be interested in numbers would be the real numbers and the complex numbers, which you'll meet in your other courses. Number theory is interested in Z, the set of integers and its subset. It occasionally deals with Q as well, but most of the time we're looking at Z and some of its subsets. You need to know how these sets are related. The set of positive integers, Z+, is a subset of the set of natural numbers, which is a subset of Z, a subset of rationals, which is a subset of the reals, and that's a subset of the complex. All these subsets are strict subsets, right? There are numbers that are in Z, that are in Q that are not in Z, as you should know, and numbers that are in C that are not in R, and so on. So these are strict inclusions. Now, there wouldn't be very much point to number theory if all we were doing was looking at the sets. We have to look at how we take elements of the sets and combine them together. You should know, of course, that we can add and multiply in all of these sets. If we add two natural numbers, we get another natural number. If we multiply two rational numbers, we get another rational number. We say that these sets are closed under addition and multiplication. And we can also subtract in these sets, apart from in the naturals and in the positive integers. If we subtract two natural numbers, we might not get a natural number out. Okay, so we can subtract natural numbers, they're just not closed under subtraction. So that's why we tend to avoid using subtraction in the natural numbers. If we want to subtract with integers, we should go to the full set of integers. Q, R, and C are very different sets from Z. They are fields, and a field is a set where you can not just add, subtract, and multiply, but you can divide. You can't divide by 0, of course, but apart from that you can divide by anything. They are fields. But we cannot always divide in Z and its subsets. And we learn this fact when very young. You learn very young that if there are 3 of you and you've got 2 biscuits, you can't divide them equally among you. You've got to cut them up in some way. What we want to look at then is what replaces the idea of dividing in Z. If you think of what would happen if you had, say, 12 eggs, you know that you could take 12 eggs and divide them among 2 people or 3 people or 4 people or 6, but but not between 5 and between 7. If you wanted to divide 12 eggs between 7 people, you'd have to make an omelette of them or scramble them or something. So what we want to do is to create a definition that tells us when we can divide in Z and when we can't. And this is the definition. It's the idea of divisibility. For two integers a and b, where by convention we assume a is not 0, we say that a divides b if there is another integer q such that b is a times q. We avoid 0 here for a because we can't really talk about 0 dividing anything. So that's why we've put it out of the way. Now we have our notation, and this is our notation. If a divides b, then we write this symbol here, which we read as a divides b. Now what you must not do is you must not confuse this, right, with a over b. Right? It's a vertical line there, a divides b. So don't get a divides b mixed up with a over b. A divides b is a statement. It's either true or false. 2 divides 12 is a statement, and it's a true statement. 7 divides 12 is another statement, and it's false. So they're statements. A divides b is a statement. A over b is typically a number, and it's usually in rationals, of course. Make sure you get these wrong. Read the right way around. If a does not divide b, then we use this way of writing it here. Right? We just put a cancelling line through the divide symbol. So we read that as a does not divide b. So if we want to use this notation then on when I was talking about distributing eggs, we said that we can divide 12 eggs among 2 people. So that's saying that 2 divides 12. And this is true because 12 is 2 by 6, or 2 by 6 is 12. So the same thing, of course. Our other examples then, I said that 3 divides 12, and 4 divides 12, and 6 divides 12, but 5 doesn't divide 12, and 7 doesn't divide 12. So that's how we would write these statements in this notation. And remember, again, these are statements, not numbers, and you should make sure you can prove them. These are very straightforward. If you want to pause the video for a bit and write down something to convince yourself that these statements are true, then do so now. Now, there are other ways of saying 2 divides 12 when you write this down, and here are some of them that we will use depending on the context and what you find useful. You can say a divides b can also be said as a is a divisor of b, or that a is a factor of b. In both these ways, and in fact a divides b originally, we're really concentrating on a, the relationship of a to b. A is a divisor of b or a factor of b. You could also say a divides b, or say something equivalent to it the other way around. You could say that b is a multiple of a, because you multiply a by something to get b, or b is divisible by a. And you'll use one of these terms depending on exactly which emphasis you want to put on a divides b. So here are some trivial results about divisibility before we go any further and look at something more interesting. And the first one is that 1 divides a and a divides a for every non-zero integer a. This is pretty obvious, right? 1 divides a because 1 times a is a, and a divides a because a times 1 is a. So those are very simple. Our second statement, simple trivial result, is that if a and b are positive and a divides b, then a must be less than or equal to b. This again is pretty obvious. You can't have 21 dividing 7. You can't have a larger number dividing into a smaller one. But notice that I do say positive here. It is important that you have positive in there because we are allowed to use negative integers, and it is true, for example, you could pick some negative numbers for which this would not be true. I'll leave you to think of an example. So let's now turn to some slightly more interesting facts about divisibility. The first is this one here, that if a is not 0, then a must divide 0. We don't talk about 0 dividing anything, but we can say that a always divides 0. And again, this is quite simple to prove. If you want to think about this for a second or two before moving on, then you can pause the video and do so. Because the proof in fact follows immediately from the definition that a times 0 equals 0. So a divides 0 for every non-zero a. Our second result is that if a divides b, then it must divide every multiple of b. So if a divides b, then a divides bx for every integer x. And here's an example. We know that 2 divides 6, so it must follow that 2 divides every multiple of 6, such as 12, 18, 24, minus 36, minus 66, anything you want. And this, again, is immediate from the definition of divisibility. And I'll leave you to write out a proof of that. It shouldn't take you more than a few seconds. Our third result, things getting a bit more interesting now, is that if A divides B and A also divides C, then A must divide B plus C and it must divide B minus C. And here's a little example for you. 3 divides 9, and we know that 3 divides 21, and so it follows that 3 must divide 30 because 30 is 9 plus 21, and it must divide minus 12 because that's 9 minus 21. I'm going to prove this result in a minute or so. But before I do that, one more interesting fact. If A divides integer B and B divides C, then A must divide C. For example, 4 divides 12 as we know, and 12 divides 36, so it follows that 4 divides 36. The proof of this is in the tutorial problems, so I'll leave you to do that with your tutor, or preferably before your tutorial. What this last statement D is saying is that divisibility is transitive. We'll study the idea of transitivity more thoroughly in the second half of this chapter. But let's go on now and prove C, that if A divides B and A divides C, then A divides, well, I'm going to prove that A divides B plus C only. I'm going to do the addition case. I'll leave you to write out the subtraction case. You should see it's trivially almost identical to this proof. So where do we begin? Well, we begin with the two facts we know. A divides B and A divides C. And the only thing we can do with these is translate them into simpler notation to actually use the definition. So that's what we do. A divides B means that the sum integer, which I'll call Q1, such that A times Q1 is B. And A divides C means that there's another integer, Q2, such that A times Q2 is C. Make sure, of course, you use different symbols here. I've used Q1 and Q2. You could use Q and R or S and T, whatever, but different symbols, please. It's a common mistake that people don't change the symbols here. So having done that, having translated our hypothesis, A divides B and A divides C, into simple notation, what do? Well, we're looking for something to do with B plus C, and the only thing that can possibly be done here is to add these two equations together. So that's what we do. We add together our two equations, and we get B plus C. Well, that must be A times Q1 plus A times Q2. And then, well, again, the only real thing we can do is to take out the common factor of A, so we do that. So we've got A times Q1 plus Q2. But in fact, this is now saying that A divides B plus C, because Q1 plus Q2 is just some other integer. So we've got B plus C is A times some integer. In other words, A divides B plus C, and that's our proof. Now we can actually put these two properties B and C together to get a rather more interesting result, which is that if A divides B and A divides C, then it must divide every integer of the form bx plus cy for any integers x and y. In other words, A divides every integer linear combination of the integers B and C if it divides B and it divides C. I said this is just a corollary of what we've already done. We just put the two definitions together. And in fact, we can generalize this too. We can generalize this to any number of integers. If we know, for example, that 3 divides 12 and 3 divides 15, and it also divides minus 9. So it must divide every integer of the form 12 alpha plus 15 beta minus 9 gamma for any arbitrary integers alpha, beta, and gamma that you like. And you should easily be able to see why this is true. It's really just using properties B and C again and again and again as necessary. But you could probably write down a general proof if you were so minded, and I'll leave you to do that if you want. Now, when we're working with integers, it's useful to have some tests to help us decide whether one integer divides another without actually having to go through all the bother of doing the division. And that's what I'm going to finish this video on, looking at a few divisibility tests, some of which you ought to know, the first two at least, and the others you'll be able to prove later on. Our first one, you certainly ought to know, is that 2 divides n if and only if the decimal expansion of n ends in an even integer. And here's an example. I've just written this number down at random by sort of typing on my keyboard. 435345835506 is divisible by 2 because it ends in 6, which is an even integer. but the next integer along, 43534583507, ends in an odd integer, so it's not divisible by 2. Now, if you need to prove this test, I'll leave you for that to do. And you can also think about how you would prove the more general result that says that 2 to the power of k divides n if and only if n divides the last k digits of n. It's not much more difficult than the original case, but worth having a go at. Our second divisibility test, again something you ought to know, says that 5 divides n if and only if the last decimal digit of n is either 5 or 0. And again, here's a semi-random number, 543534583550. That number is divisible by 5 because it ends in 0. But the next number here, 543534583553, well, that's not divisible by 5 because it doesn't end in either 5 or 0. And again, I'll leave the proof of the test for you to do if you feel you need it. It shouldn't take you very long. Our next test, in fact, is actually two tests which I've put together, says that 3 divides the natural number n if, or the number integer n, if and only if the sum of the decimal digits of n is divisible by 3, and similarly for 9. 9 divides n if and only if the sum of the decimal digits of n is divisible by 9. Now, here's an example, 918747, that's divisible by 9. Of course, if it's divisible by 9, it must be divisible by 3, because 9 plus 1 plus 8 plus 7 plus 4 plus 7, you add it all up, it's 36. And you all ought to know that 36 is divisible by 9, and clearly by 3. In fact, if you weren't sure whether 36 were divisible by 9, you could add the digits 3 and 6 together, and you get 9, which is clearly divisible by 9. So you can repeat the test if necessary. The proof of this test are part of the tutorial problems in Chapter 3 of the course, so you can have a look at that then. In fact, we usually use this idea, or at least the second one, 3 dashed here, for divisibility by 9, in the sense of casting out 9s, which some of you may have heard of. You go through the numbers, and every time you have a sum that adds to 9, you basically throw it away, and if you, in adding the numbers, the digits in turn, you get a number that's got 2 digits, you just add together. So with this number here, 918747, well, 9 is divisible by 9, so throw that away. 1 plus 8 is divisible by 9, throw that away. 7 plus 4 is 11. Well, you then contract that to 1 plus 1, which is 2, and 2 and 7 is 9. So again, that's how you would prove that 918747 is divisible by 9 by the method of casting out 9s, as it's often known. Now, my last divisibility test is for divisibility by 11. And it says that 11 divides n if the alternating sum of the decimal digits of n is divisible by 11. Now, by alternating sum, I mean you don't just add the digits, you add, then subtract, add, subtract, add, subtract. It doesn't matter which direction you do this from, by the way, from the largest to the smallest, you're going to get the same answer either way. It's an alternating sum. So here's an example, 1, 2, 3, 2. That's divisible by 11, because 1 minus 2 plus 3 minus 2 is 0. And I'll leave you to work out what you get when you divide 1, 2, 3, 2 by 11. Get your calculator out if you don't believe me, and you'll see you get an integer. Now, the proof of this test follows more or less the same pattern as the proof in Chapter 9, and you'll be able to do that in the material once you've looked at proof theory in Chapter 3. Now, with these rules, you can find some small factors of numbers without having to resort to your calculator. And I invite you next time you're sitting on the bus or the train with nothing better to do, put your phone away for a change and try and find small factors of, say, the number on your Opal card. Ignore the decimal points, of course. And here we see 2 pictures of some cute totals on my own Opal card, and I invite you to try and find or check off some small factors of the 2 numbers that we're shown here, 2310 and 2016. As I mentioned earlier, it's trivially true that 1 divides a and a divides a for every integer a. And if we were trying to find numbers that divide, integers that divide some integer that would be given, and we got to the case of a factor that had that property, that the only things that divided it were 1 and itself, then we'd stop. We wouldn't need to go any further with that. Now, what we're going to look at in the next chapter are integers for which this is the case, where the only true statements, true divisibility statements we can write are that the number is divisible by 1 and by itself. And these numbers are known as primes.